This meeting is being recorded.
In section 410, we'll take a look at the conformations of cyclohexane. So we're at our six-membered ring now. So cyclohexane, we're told, can adopt a variety of conformations, but it is most stable in this specific chair conformation. So we'll spend most of our time talking about that, but we'll also talk about some other conformations. The chair and the boat are commonly mentioned as the two main conformations of cyclohexane, but we'll see that why the chair conformation is much more stable. It ends up having much lower energy in either of these two chairs shown down here than our boat. They're about 30 kilojoules per mole difference in stability. And then we'll also see some of these other half conformations. We see a half chair. This is our highest energy. So our cyclohexane would spend its least amount of time in that conformation. And then we have this twist boat that's kind of in between the half chair and boat conformation. So that's around 23 kilojoules per mole difference than our chair conformation. So why is the chair conformation so stable? Well, it really has not much ring strain overall. So there's no real angle strain because they're very close to that ideal 109.5, all of our bond angles. And there's not much torsional strain because if we look at this bond and this bond here, for example, they're adjacent. And we see that along the whole molecule, that all of these hydrogens will be adjacent to another. So there's no torsional strain for that reason. So because of this, this cyclohexane chair conformation, and we can see with the Newman projection here more clearly, doesn't have that ring strain that the other conformations have in varying amounts. So let's take a look here. If we wanted to draw this chair conformation, they tell us that we should start by doing a wide V. Maybe I'll do a little wider V, then drawing down like this, drawing up, and then we do the same thing over here, down and then up. And it takes some practice to get used to, but your chair will look something like this. Yours probably look better than mine if you actually draw on a paper. So they have you follow these lines, drawing pairs of parallel lines so that you end up with this chair conformation. And we're going to see here, right, those three sets of parallel lines will guide us when we have to draw our axial and equatorial positions. So let's take a look at what that means here. So an axial position is when you have a bond that is parallel to the axis or the central line that I drew there, the central axis to your chair conformation. And then an equatorial position is in a similar manner to the equator, if you will, of your molecule. So equatorial positions will match up with this line that I drew horizontally, and then axial positions will match along that vertical line. So let's see what this will look like. So after you've drawn your chair conformation, if you need to add an axial substituent, this is what we would do. We would draw this line here on our first carbon. Then we're going to alternate around our ring, going up and down. So then we go to this point here, we go down. And we can see this point is kind of pointing down. So that tells us, again, to put our axial position pointing down there. And then this next carbon, we see that carbon is even pointed up. So we draw our axial position up. And then we end up with this in the end here. After going around all the carbons that are pointed up, we'll draw our axial positions up. And then the three that are pointed down, we'll draw down. And then again, they're kind of parallel to this central axis of our molecule, of our cyclohexane ring. So let's draw those equatorial groups. We're going to look at the parallel lines in red here, and we see that if we have this one here, say, we have that parallel line. We kind of draw our substituent in that same fashion. So not quite horizontal, a little bit lower than the horizon, right? We have our equatorial positions pointing down. On these two carbons, we have one pointing up. So we alternate again with the up and down position. So these would be up equatorial, this would be a down pointing. And we'll see why this is important when we have to translate a flat molecule that's shown with wedge and dash into something in a three-dimensional space. That's good to know. So let's take a look here at this next slide. This brings us to monosubstituted cyclohexanes, and we'll continue with this section because we just introduced our chair conformation, and that if we place a substituent on an axial position, we can see that there's actually this process of ring flip that can occur where our axial position, this carbon here, flips downward. This carbon here would flip upward. So the first carbon that I moved with the axial substituent has moved down here. And we see that this has become now an equatorial position for the substituent, right? Based on this line here being parallel to this line here. And then we see that this second carbon that I pointed out that flipped is now up here in our ring. So this ring flip occurs with our chair conformations, and this would be by rotating carbon-carbon single bonds within the ring. And as noted, all the axial substituents would become equatorial and vice versa. So if we had our equatorial substituent here, we see this carbon in the front is rotating to the right. That carbon in the back is also rotated. And we end up with now that equatorial substituent being axial. And if we had others, they would switch positions as well. So let's take a look at when we start adding substituents. So we have a methyl substituent shown in each our axial and equatorial position. And we're told that it's not really in equilibrium so much, but this position on the right is favored about 95% of the time. It's more stable. It will be a lower energy compared to this other position where the methyl group is only in the axial position, and this only occurs about 5% of the time. So we're going to see why, due to some steric interactions, how they destabilize the conformation on the left. So we're going to see that right-hand conformation, or that, that right structure conformation about 95% of the time. And this because the structure that's on the left experiences this steric strain from that substituent being in the axial position. So we see this illustration here. When we have this axial position of that X, that substituent, its electron cloud is kind of, all this space here being taken up, and these hydrogens, their electron clouds, will interact and kind of destabilize or have that repulsive effect on the substituents. So we can see this 1,3 diaxial interaction occurs within our ring from hydrogen atoms on the carbon 3, and then say we have a methyl substituent on our carbon 1. That's where we would end up with that name from. On carbon 1, the methyl group; on carbon 3, those two hydrogens. And we can see this illustrated in the boxed-in structure as well, this kind of steric strain from a substituent. So this is when they are in a gauche position or conformation. We see this present in the axial position specifically, but it would not be in when the methyl group is in the equatorial position. So we can see here there's none of that steric interaction that there is with the axial position. So this is the equatorial position shown down here, where there's that lack of gauche interaction. So that's why we see the percentages of time where we have one conformation over the other. And we can see, depending on our substituents, we get larger and larger as we go down our list here until we get to this tert-butyl group down at the bottom. That's our largest. But we see even with a chloride substituent, we still could have that 1,3-dioxyl interaction, and then that would result in an equatorial to axial ratio of that substituent at equilibrium to be 70% of the time for the chloride to be in the equatorial position, and then 30% of the time the chloride would be in the axial position. So again, this has to do with that steric strain, that 1,3-diaxial specific interaction, and that would cause this structure to have about a 2 kilojoule per mole higher energy when in the axial position than equatorial. So that's how you can interpret this graph here. And that is everything from these two sections. And we'll see some similar information in our Lab 04 on stereochemistry.